Good morning. All right, last week we talked about a gradient. Just to recap what a gradient was, if you've got a function of two variables, the gradient of f of xy is equal to the vector formed by your x derivative comma your y derivative. In the same way, you could have a gradient of a function of more than two variables. Let's say x, y, z, and that would be your x derivative, still a vector, your y derivative, and your z partial derivatives. Okay, so now, and then we talked about one of the applications of the gradient that's going to help us find the directional derivative. Okay, your directional derivative of a function, du of f, is equal to your gradient of your function dotted with a unit vector that's in the direction that you want to travel. Okay, you want to find your directional derivative in that direction. Okay. Now, probably the biggest application or significance of the gradient is that if you want to be traveling in the direction of maximum increase of a function, so you want to pick the direction here that's going to maximize your directional derivative. Let's see if I can get that a little bit more focused. That direction is always going to be in the same direction as the gradient. Okay, and the math to prove that is fairly simple. If you want to maximize this thing, now this is a dot product, so it's going to be a scalar. If you want to maximize this thing, remember how you find a dot product. So it's going to be the x derivative, comma, the y derivative, and then you dot that with some unit vector, or it could be, three-dimensional. Okay. Or the other direction, the other definition for a dot product is the magnitude of f times the magnitude of u times the cosine of the angle between them. Okay, so the significance here is that if you're finding a directional derivative, the directional derivative, this thing is always maximized when these two things are in the same direction. So you're taking a derivative in the direction of the gradient. Okay, the math is pretty easy. This quantity is maximized when cosine is equal to 1, which means cosine of your angle equals 1, which means your angle is 0. Okay, so if the angle between these two is 0, that's when you're maximizing your directional derivative. Okay, the other significance is that the maximum, if you want to maximize the directional derivative, it's just going to be equal to the magnitude of the gradient. Okay, if u is any other direction, then when you find the directional derivative, you're going to have this times some angle that often is going to be less than some angle where the cosine is going to be less than 1. But if it's equal to 1, it's maximized, and if it's equal to 1, your maximum directional derivative of your function is equal to the magnitude of the gradient, times the magnitude of this unit vector, which is 1, times the cosine of the angle between them, which you know that angle is 0. So your cosine of 0 is 1. So this is your maximum directional derivative. Okay. Now let's talk about why this makes sense, because really it does make sense. Remember, we looked at this picture right here. Okay, let's say you're looking at. We got a little bit of a glare there. Maybe I can put that like that. Maybe see that a little better if I do that. Okay. So if let's say I'm traveling. Let's say I'm. Where is the United States? It's right here. Let's say we're here in Chicago and we're traveling along this level curve. Okay, what's your rate of change of your function as you travel along a level curve? Well, the rate of change of your function is 0 because your value of your function doesn't change as you're moving along a level curve. Any one of these level curves, if you travel along the level curve, you're staying at a constant value of your function. The temperature here is 20 degrees Celsius. So if I travel along here, my rate of change is 0. But let's say you're over here and you want to get to warmer weather as quickly as possible. You're not going to travel along your curve. You're going to travel the direction to get as quickly as possible to that next level curve, okay, which is going to be a warmer temperature. Is that a warmer temperature? Yeah, they're getting warmer as you go south. So you'd be traveling perpendicular to your level curves, okay? So your gradient is always going to be perpendicular to your level curves, okay? Because the gradient is the direction of maximum increase. And that's a picture with just a two-dimensional function. Now, remember when we had this function here, we looked at this one. And this would be, these are level surfaces. So here's your function, f of x, y, z equals x squared plus y squared plus z squared. Setting this equal to 3 different constants. We set that thing equal to 9 or to 4 or to 1. We got these level surfaces, okay? And if we want something perpendicular to a level surface, well, that's going to be in the direction of the gradient. So the gradient is going to be perpendicular to, basically perpendicular to a tangent plane to each of these surfaces. Think about if you're traveling along this yellow surface where the constant value of your function is, I think that one's 4, okay? Your rate of change is going to be 0 as you travel along this yellow surface, okay? But if you want that rate of change to be as large as possible, if you want to maximize it, you're going to go perpendicular to that so you can get to this one, the blue or bluish purple one, as quickly as possible. Okay, so your gradient is perpendicular to your level surfaces. Your gradient would also be perpendicular to any level curves. Okay, so let's look at an example. Example 5. Okay, so you've got this thing, some function t. The temperature in degrees Celsius on the surface of a metal plate is T of xy is equal to 20 minus 4x squared minus y squared. They might ask you a question, okay, where x and y are measured in centimeters. In what direction from the point 2 comma negative 3 does the temperature increase most rapidly? Okay, well, we know the temperature is going to increase most rapidly when we're traveling in the direction of the gradient. Okay, so we have to find the gradient of this function. The gradient of t is going to be equal to the x derivative, so negative 8x, y derivative, negative 2y. Okay, so the gradient at the point 2 comma negative 3 is equal to negative 8 times 2, negative 16, and negative 2 times negative 3, so positive 6. Okay, we have a really good picture in the book. So this thing, if we set this thing equal to a few different constants, it's this on page 925, these are level curves for this function right here. Okay, setting it equal to a few different constants, we get these ellipses. Okay, so you're setting that equal to, I don't know if it shows what you're setting them equal to, but your different level curves of this function, setting them equal to different c values, you get these ellipses. So at the point 2 comma 3, so that's a 3 right there. So 2 comma 3 is this point right here. Okay, if you want to go in the direction of greatest increase, you're going to be traveling perpendicular. So you could draw a tangent here, perpendicular to this level curve at this point, at that instant. So that was, what do we get? Negative 16, positive 6. So negative 16, positive 6. Obviously, they didn't draw, they just drew the direction of it. They didn't draw that entire vector. Okay, you just wanted a vector that's perpendicular to your level curve, and that's going to give you the direction where you're increasing most rapidly. Now, in the same way, if you want to decrease most rapidly or increase least rapidly, as I think the way they say it in here, they say the direction of minimum increase of x is going to be the opposite direction. Okay, so it's going to be negative. So I'll write down these two things. These are the two things that are most important about your gradient. Okay, the direction of maximum increase of f is given by the gradient of f of xy, okay, or xyz, okay, and the maximum value of the directional derivative of f of xy is the magnitude of your gradient of f of xy. Okay, so that's one point. Next point is the direction of minimum increase of f is given by the opposite of the gradient of f of xy. Okay, and the minimum value of your directional derivative is the opposite of the magnitude of the gradient. Okay, the minimum value of your directional derivative. Okay. All right, so we're going to look at example 6 now, which is basically a continuation of example 5. In example 5, all we were trying to find was a vector that's in the direction of maximum increase at a given point, just at one single point. Now this is asking us, this one is asking a little bit more. It wants the path of that particle. So notice as you move here, now once it gets to this curve, it's not perpendicular to that level curve anymore. So this is actually going to bend. If you look down here, I show a really good example. So as you're moving closer, you always want to go, obviously you want to get to that hottest point, okay? But you're going to travel always perpendicular to your level curve. So as you get to this level curve, it's going to bend a little bit. So it's perpendicular to each of these tangents to the next level curve, okay? Now, the path of the particle, let's say the path can be represented by a position vector, r of t equals x of t at y of t, okay? And then if you take the derivative, you're going to get a tangent to that curve. You get a tangent to that curve, and the tangent to these curves should always be in the direction of the gradient, okay? So we've got something that looks like this. Let's go to example 6. Oops, almost dropped my book. Okay, so on example 6, we're going to say that we've got r of t is equal to some vector x of t, y of t. Okay, so r prime of t is going to be tangent to that curve. So that's going to be dx dt, comma, dy dt. Now we know that these are always in the direction of the gradient, okay? And our gradient, again, was the gradient of f was equal to negative 8x, negative 2y. Okay, so we're going to set these equal, we're going to set these equal. So we get dx dt is equal to negative 8x. And we have dy dt is equal to negative 2y. So we want to use this to come up with some kind of a curve that only has x's and y's in it. Okay, so this is something we're going to think like we're going to separate your variables. Let's get the x and the dx together. So let's move this over here. Oh, and actually these don't have to be equal. They just have to be in the same direction. Okay, so let's set them equal to a constant. Okay, we can use the same constant for both. It's just going to be a constant multiple of this thing is going to be equal to the gradient. Okay, so we've got, let's get the dx we need over here. Let's move this over to the other side. Okay, so the dx over negative 8x is going to be equal to dt over k. So we need these two together. We need the y and the dy together. So dy over negative 2y is equal to dt over k. And since this and this are equal, we can now set these two equal to each other. Okay, so dx Actually, let's write it this way. So -1/8 times 1 over x dx equals -1/2 times 1 over y dy. Okay, we're going to integrate both sides. So that's going to be -1/8 ln x equals -1/2 ln y. We could say plus a constant. Okay. And then when you, let's do this, let's multiply both sides by -8. Okay, so multiplying by -8, we're going to get ln of x equals, and that's going to be 4 ln of y plus c. We call that a c1 now, which is multiplied by a -8. Okay, so we could do, what do we want to do? So e, let's do e. Let's raise e to the left side. Ln x equals e to the right side. 4 ln y plus c1. So that's going to be x equals 4 ln y. So that's going to be ln y to the fourth. So that's going to be y to the fourth times e to the c1. So let's just call it c2. And we basically get x equals c2 y to the fourth. Okay. And now using the point 2 comma -3, we can solve for c. Okay, so that's going to be 2 equals c2 times y to the fourth. So that's going to be times 81. So c2 equals 2 over 81. So what we're going to get is x equals 2 over 81 y to the fourth. So that is going to be the path of our curve. All right. And I think that's all. Do we want to do another one? I don't think we need to do another one. Example 7 is kind of interesting if you wanted to take a look at that. Find a normal vector to a level curve. Okay, so they take this thing, sketch a level curve to c equals 0. So if you set this thing equal to 0, you simply get y equals sine x. Now notice what they did. This is y equals sine x. It's a cylinder. Okay, it's kind of weird how they drew that here, but you're drawing a cylinder. And you know that the gradient at any given point on this surface is going to be perpendicular. So they found a whole bunch of gradients at different points on here, and it's kind of neat they did that. So you can see for each of these, if you drew them to the curve, each of these vectors is going to be perpendicular to your curve or your surface at that point. All right. Okay. And that's about it. Thank you for watching. I hope you enjoyed.